Hello everyone. Next we are going to discuss the mathematical implications of entropy and its physical significance. We have to start from the combined mathematical form of the first law and the second law of thermodynamics. The mathematical form of the first law of thermodynamics is dq equals to du minus w. So if only mechanical work, that means pdv, is involved and the heat change is irreversible in nature, then the mathematical form can also be written as dq reversible equals to du plus pdv. So this is equation number 1. On the other hand, the mathematical form of the second law, just we have derived, it is equal to ds equals to dq reversible by t, and if this t is multiplied with ds, then it becomes tds equals to dq rev. So thus we get equation number 2, and we find that the left hand sides of equation number 1 and 2 are same, so the right hand sides would also be equal. This way we can write tds equals to du plus pdv, or by rearranging we can write du equals to tds minus pdv. So this way we get equation number A. We are going to have 4 equations, equation A, B, C, D. These are the fundamental equations of thermodynamics for closed system, and right now we have obtained one of them. That is why this is not 1, 2, 3, this is equation number A. Okay, and if this combined mathematical form of the first law and second law, if these two are combined with the Clausius inequality, that means this is actually applicable for reversible process, but for irreversible process there should be an inequality. Okay, so in that case the Clausius inequality, when it is merged with this one, then we can also write, instead of dq we can write tds, and that dq is irreversible dq. Okay, and tds in that case must be greater than du plus pdv, because this would be applicable for irreversible process, du plus pdv. So this tds value would be greater than du plus pdv, but this equality sign is applicable if the process is reversible instead of irreversible. So both the possibilities are merged here. So for both reversible and irreversible changes we can write tds greater than equal to du plus pdv. So this is the combined mathematical form of the first law of the thermodynamics, the second law of thermodynamics, and the Clausius inequality. And if this equation is rearranged, we can also write du is less than equal to tds minus pdv. Now from this perspective we can think that why is this inequality sign, or why is this equality sign? Actually inequality sign indicates irreversibility of the system, and irreversible means it is a spontaneous process. On the other hand, the equality sign indicates reversibility of the system, and reversibility is applicable for the system when it is attained equilibrium. Okay, so this is very important. So spontaneity of a system, or spontaneity of a change. How does a change takes place spontaneously? It takes place spontaneously only when it is irreversible. So the change that takes place automatically in a system without the aid of any external agency is termed spontaneous process. So this is the definition of spontaneous process. I repeat, the change that takes place automatically in a system without the aid of any external agency is termed spontaneous process, and this action is unidirectional or irreversible. And definitely for spontaneous process the Clausius inequality is applicable, that is dq irreversible by t must be less than ds. Okay, and definitely for non-spontaneous process, which is actually reversible in nature, for that case dq must be dq rev, and in that case dq reversible by t must be equal to ds according to the second law of thermodynamics. So these two are the conditions for spontaneity and equilibrium. Okay, now one of the corollaries of the second law. So the second corollary of the second law of thermodynamics was entropy of the universe is always increasing. So how we can explain this corollary? Suppose this is the system and this is the surrounding. Okay, and the system has higher temperature at T1 and the surrounding has lower temperature at T2. So the system is releasing delta Q amount of heat. That is why, since it is releasing, it is negative sign, and that amount of heat is being absorbed by the surrounding. So it is given plus delta Q. Okay. So when the body at higher temperature, that is T1, it comes into contact to a body at lower temperature, that is the temperature is T2, then some heat flow. This is not the, this is then. So when you're taking note, make the correction of the typing error. It is then. Then some heat flow, say dq, delta Q, takes place. Okay. So the entropy change for the body at high temperature, suppose this is the body at high temperature, this is equivalent to the system, the entropy change must be delta S1, and which is definitely heat change by its own temperature, that is T1. Okay. So it is minus dq by T1. Okay. And for the surrounding, that means the body at lower temperature, it is ds2, and that is dq by the own temperature of the surrounding. That means the second body, that is dq by T2. Okay. So what is the overall entropy change of the combined system? The overall entropy change of the combined system must be equal to the summation of the entropy change of the first body and the entropy change of the second body. That means delta S1 and delta S2 summation. Okay. Now we know the value of delta S1, which is minus delta Q by T1, and that of the second body, delta S2, it is delta Q by T2. Okay. And if minus delta Q is taken as common, then you will get here 1 by T1 minus 1 by T2. Now this negative sign, if here multiplied with 1 by T1 and minus 1 by T2, then it will reverse their order. That means it will become 1 by T2 minus 1 by T1, and the final result is T1 minus T2 over T1 T2. Since T1 is greater than T2, then the overall quantity has some positive value. Okay. So if system body 1 is equivalent to a system, and if body 2 is compared to be equivalent to the surrounding, then if some system releasing some heat to the surrounding, then the overall entropy would increase, and the combination of the system and the surrounding is nothing but the universe. Therefore the entropy of the universe is always increasing, and this second corollary of the second law of thermodynamics has been proved mathematically. Now move on to the relationship between enthalpy and entropy. We have already obtained the relationship between internal energy and entropy, temperature, pressure and volume, such that du equals to TdS minus PdV. That relationship has already been obtained as one of the fundamental equations of thermodynamics for a closed system. Now we are going to obtain same type of relationship in terms of H. So in order to do this, let's start from the mathematical expression of H, which is nothing but equal to U plus PV. If differential of both sides are taken, then it gives dH equals to du plus PdV plus VdP. Now we know that du equals to TdS minus PdV. Okay, so let us put this value here. Instead of du, we are putting here TdS minus PdV, and this PdV plus VdP remains the same, but it is found that these two are same, having opposite signs, so these two are cancelled by each other, resulting in TdS plus VdP, that is equals to dH. This relationship is another fundamental equation of thermodynamics for a closed system. So we have the equation dH equals to TdS plus VdP, and that is the fundamental equation number B. So we have two more equations to be obtained in terms of A and G. A is the work function or the Helmholtz free energy, G is the Gibbs free energy. So later we must be discussing them, but not now. For now this lecture is over now. So thank you and have a nice day.